joining. My name is Philip Howard. I am the project manager of the ESSF project, and I'll be hosting this webinar. My colleague Natalia Marsh, who you will see here, will be the main person delivering the training today. Just to get started, if we could move to the next slide, please. Quickly, this is the agenda. We'll just do a few practical remarks and some icebreakers just to find out who we have here. I mentioned that I'm the project manager of the ESSF, so I'll tell you what that means. We'll also give an introduction from ESA, and then we will dive into the main training session of this. If we go to the next session, this session is being recorded. Just to anticipate the common question, yes, both the slides and the recording will be shared via email afterwards, or you can get the link from the shared document that we will send out afterwards. Because it's being recorded, the usual things apply. Please keep your microphone off. If you have any questions, feel free to raise them in the chat, and we will respond either in the chat or whenever there's a suitable break comes along to respond. So just as an icebreaker, let's ask a few questions with Menti. You can follow the QR code here, or you can join menti.com with the use code that you see there, 35834420. So very simple question, where are you from? We just want to get a picture of who's joining here. If you could join in Sweden, Poland and Sweden, very well represented here, but quite a few. Netherlands coming in strongly. Good for you. Okay, it's good. So mostly European that I've seen, but with a very, very good cross-representation across Europe. Oh no, there's a couple of non-European ones there. I see Indonesia at least. Okay, if we could maybe switch to the next question. So just to give a bit of a word cloud, understand where we are, is just to understand what your interest in Earth observation is in 1 or 2 words. Now, I know this is the sort of thing that's very difficult to summarize in 1 to 2 words, but if you could try, well, money was the first one, that's always one. SDGs, okay, biodiversity. Ecosystem statistics, good, conservation. Okay. Again, that's very useful. So I'm glad to see that statistics is the most common one, which means you are all in the right call. Otherwise, it might have been a problem. Okay, I think that is very useful, just to give us there. It's still coming in, so we'll keep that open just for a minute or two. In the meantime, I will just give a quick introduction to what exactly the ESSF is. It is called the Stakeholder Engagement Facility. We are supporting the European Space Agency, and Federica from ESA will talk in a minute. The idea is that we want to support ESA's engagement with a wide range of stakeholder communities in order to promote the use of Earth observation and help to understand what problems people are trying to solve with Earth observation. So on the one hand, we take the tools and the services that have been developed by ESA, but also by the space industry in general, and we promote these to users through outreach, through training, through capacity building. But at the same time, we talk a lot to users, we collect their feedback, their needs and the requirements in order to better tune what the future development of Earth observation will be. Where the team is led by Evenflow, a consultancy based in Brussels. We also have Serco as our technical partner, and the European Association of Remote Sensing Companies provides our link to the wider Earth observation ecosystem. If we go forward 1 slide, please. This is the sort of things we do. Typical problems faced by users. It could be awareness, they don't know what exists, in which case we showcase them. It could be that they know the solutions exist, but they don't know how to find them, how to get started, in which case we can provide guidance, support, training. And then finally, they need technical support to integrate the service into the workflow. And again, we can support there. If we go forward 1 slide, you may have met us. We have actually been attending several events such as the EFGS, the NTTS, the UNGGIM meetings. So quite possibly we've already met you and had a chat to you. If you haven't, we are keen to know much more about the needs of the statistics communities. We want to know what problems you're trying to solve and how you think Earth observation might help. And we want to know what your experience has been and where you've had difficulties. There will be a short survey after this webinar series. It would really help us if you can fill this in. But then do please feel free to reach out directly if you would like to discuss more. We really do encourage people to come and talk to us. And on the next slide, again, you don't have to take this now, it will be circulated afterwards, but here are our contact details along with links to our website and to the LinkedIn. So that was all I wanted to say about the project. I will now hand over to Federica Marando from ESA, who will just say a few words about what ESA's role is here before we get into the main event. Federica.
Thank you so much, Phil. And good afternoon, everyone. My name is Federica Marando from ESA. I'm very pleased to welcome you today to this training, exciting training with this brief introduction. And the idea will be to provide just a bit of context behind this training and also a bit of the strategy and the idea looking forward from the ESA perspective. But I would like to start with just a few words of context of what is ESA. It is an intergovernmental organization with the mission of advancing space research and technology of its member states with peaceful purposes. And we are based in the Department of Earth Observation Programs at ESA, where our core business is really to, from one side, operating and managing satellite Earth observation missions, but also to enable the use of this raw data coming from the satellites. So we want to make them fit for purposes for specific applications, including and especially, in this case, official statistics. And for doing so, we try to adopt always a very user-centered approach. So we really want to develop end-to-end solutions that can respect the rigorous standards of official statistics. So in order to do so, we work very closely with the users, such as in this case, for instance, national statistical offices. We see with pleasure that we have many representatives today of NSOs, also environmental agencies, for instance, or mapping agencies, and also, of course, the broader community working on official statistics. So we really want to learn from your experience, from your background, to facilitate the use of Earth observation into these operational practices. So today, this training is really a core component of this capacity building mandate that we have. And so, of course, we recognize that the gap between the raw satellite images and what is actually a validated and a useful policy indicator, statistical indicator, can be actually technical and also resource intensive. So with this training and this series of training provided by SEF, we really want to empower the statistics community to take the full ownership of the whole production process. And another important pillar of this activity is also a consultation process that is ongoing with the statistics community. So your feedback is really crucial to inform our R&D roadmap. So we want also to build this long-term partnership with NSOs, with the statistics community. And to this end, I would like to briefly share with you that and invite you, of course, to our upcoming conference, which is called StatEO 26. It is our upcoming Earth observation for statistics, official statistics, conference taking place from the 5 to 7 May of this year in our ESA Center for Earth Observation based in Frascati near Rome in Italy. So this conference is co-organized with other institutions such as European Commission services like Eurostat, UNECE, OECD, the European Association of Remote Sensing Companies, FAO, and other institutions. Next slide, please. So just a brief overview of the objectives that you will see in the conference in the form of different sessions. So it will be really focused on analyzing and see how Earth observation can enhance the granularity of key statistics metrics. I hear a bit of echo. I don't know if it's me or something else. And also how Earth observation can support the actual policy implementation. And finally, also, you will see a range of new solutions based on Earth observation and how they can support official statistics reporting. Next one, thank you. The idea of the target audience, as I said, is of course the wide community of experts working on the interface of Earth observation and national and official statistics, like national statistical institutes, environment agencies, mapping agencies. But the conference is not restricted to Earth observation or statistics experts. Actually, on the other hand, we want to really encourage this exchange between different perspectives and backgrounds so that you can inform us with recommendation that we would like to gather at the end of the conference. The structure then of the conference is, as you will see, is very different. So we have a plenary session with high-level discussion at the start of each day. Then we have the more classic kind of sessions, thematic sessions that will deep dive into specific domains of application of Earth observation for statistics, such as agriculture statistics, environmental economic accounting, urban areas, land use, land cover, and so on. Then we have another kind of format, which is the workshops. So this is very participatory kind of session, like roundtable discussions or breakout rooms, where we want really to have a bottom-up approach to get your ideas and your feedback on board. And we will also have demonstration sessions where there will be also the CEF team here that will showcase tools and provide trainings, maybe something along the line of what will be showcased in these sessions, or maybe something different that is tailored on the feedback that you will provide on this specific training. And finally, of course, the post sessions. Next one. So this is, yeah, next one. I still see, yeah, thank you. Okay, just to give you an overview of important days to mark on your calendar. So we are approaching the deadline for the submission of the abstract, which is next week, 25th of January. And then, yes, you can see from the table, the registration will remain open until the 30th of April. So don't miss this opportunity. We are really looking forward to see you all in this conference, either as a presenter or just attending and see what's going on in this community, which is emerging. And then, without further ado, I will leave you to the CEF team for this great training, and I wish you all a productive training session. Thank you.
Thank you, Federica. So I will now pass over to my colleague Natalia Marsh from Circle, who will present the main training. Just maybe as a quick introduction, this is the first of 3 sessions that we have planned. The intention of this session is very much to give you the basics of Earth observation for people who are new, but we also hope that some of the people who've already used it will learn something themselves, because often you can start using it while missing some of the basics of the underlying technologies that go into this. We will then follow this up next week with a practical session around how to get started in accessing the data and manipulating the data. And then finally, the third session in 2 weeks' time will be around some of the examples that have been developed within the Earth observation community, things like SDG monitoring, agricultural statistics, and ecosystem accounting, and it will be your chance to really see the full power of the Earth observation in action. We were obviously open to other requests. So if anybody has anything else that they were expecting to see but didn't, then please do follow up with us directly. And with that, I will hand over to Natalia. Natalia, please.
Good afternoon, everyone. I hope you see my screen well. Please, someone confirm.
Yes, we do.
Yes. Okay, perfect. So today we are going really to discuss the very basics of Earth observation. Maybe some of you already know about it, but I consider it being an extremely important part because today's session will help you to understand where to find Earth observation data, how to access it, which parameters or properties of Earth observation imagery you should consider when selecting a source of information for your projects or processes. And also, I'm happy to see some faces from our previous training, which finished in December. It was a training on the use of Earth observation for biodiversity nature conservation. Hello, Anton. Nice to see you again. Okay, let's start. So the very first thing, which I think it's very important to cover, is what is actually Earth observation. Very often you would hear terms like remote sensing, Earth observation. Are they the same or they're slightly different? So let's see. Remote sensing is the science of obtaining information about objects or areas or processes from a distance, typically from aircrafts or satellites, whereas Earth observation refers to the use of remote sensing technologies to monitor land, green areas, and the atmosphere. The history of Earth observation started really long time ago. For example, in 1862, a French photographer with the nickname Nadar started trying to capture aerial images of the town he was living in from a hot air balloon. And an example of this image you can see on the slide. And later on, like by 1914, a German engineer created a small camera which could be installed on a pigeon for them to fly around the city and make pictures. And again, you see an example of those on the slide. So interest of people in getting this type of information, like picture of Earth surface from above, started really, really long time ago. Of course, now we are in a new era, more modern one, and we have more modern remote sensing sensors carriers. For example, airplanes, UAVs, satellites, and so on. Each of those carriers, they have their advantages and disadvantages. For example, UAVs give very detailed data locally, while satellites provide global and long-term monitoring. Drones and airplanes are more expensive and less effective than satellites because they cover only small areas at a time. They require fuel, pilots, or operators, and repeated flights to monitor changes. Satellites, once launched, can observe huge areas regularly and consistently at a much lower cost per square kilometer. The Earth works like a connected system. Land, water, air, and life interact constantly, and change in one part affect the others, of course, and satellites helps us see not just the changes, but also how everything is linked. ESA, European Space Agency, has developed many Earth observation missions. Each one focuses on monitoring specific systems like oceans, land, or the atmosphere. And together they help us understand climate and the environment. And of course, the most interesting and very valuable part of this ESA ecosystem of Earth observation missions is a Copernicus mission. This Copernicus program is built around the Sentinel satellites developed by European Space Agency for the European Union. Each Sentinel is designed for a specific purpose. For example, Sentinel-1 uses radar to see through clouds, and we will discuss it further to understand more how it works. Or, for example, Sentinel-2, which provides high-resolution optical images for land monitoring, or Sentinel-3, which focuses on oceans and atmosphere, and so on. Together, they provide free and open data that supports everything from agriculture and forestry to the disaster management and climate monitoring. Alongside with Sentinels or Copernicus mission, Copernicus program also uses data from so-called contributing missions. These are national or commercial satellites owned by ESA member states or international partners. They provide additional coverage, higher resolution, or specialized measurements. Again, if it's not very clear what are those special measurements or higher resolution, it will be discussed further on. By combining Sentinel data and contributing missions data, Copernicus ensures continuity and adds value for applications such as energy, emergency response, urban planning, environmental monitoring, and many others. Now I would like to discuss in deeper details each and every of existing Sentinels. So there are several. Sentinel-1 is providing radar imaging. It works day and night. It can penetrate clouds. It's ideal for monitoring of land deformation, ice, and disasters like floods, for example. Sentinel-2 provides high-resolution optical imagery. It's great for land use, agriculture, vegetation, and water monitoring. Sentinel-3 focuses on oceans and atmosphere, measuring sea surface height, temperature, color, as well as landed atmospheric data. Sentinel-4 is an atmospheric mission carried on Meteosat, monitoring air quality, pollution, and gases over Europe. Sentinel-5P is also mission for atmospheric monitoring, measuring trace gases like nitrogen dioxide, ozone, and methane. Then there is also, of course, Sentinel-6, which is dedicated to oceanography, measuring sea surface height with very high precision to study sea level rise and climate change. Apart from those different Earth observation missions launched like by European space agencies, there are many other space agencies around the world which have their own Earth observation missions, of course. And one of the interesting ones, which I would like to tell you about today, is Lancet mission by NASA. It's the longest running Earth observation mission, which is going back to the 1970s. So currently, archive of this mission is providing more than 50 years of continuous observations of Earth's surface. So if you want to study the change of something which started like back in 1980s or 1990s, you could use Landsat for this because it has global coverage. It never stopped. This mission never stopped. It's still ongoing. So this data source is for real extremely valuable. Now I would like to move to the main source of energy for Earth observation. So for us to understand how Earth observation works, how satellites can detect all these various types of information and why we can trust this source of information, we need to understand how the physics behind this process, how it works. So the main source of the information for Earth observation is electromagnetic radiation. There are three types of energy taking part in this process. It's incident solar energy, basically the solar light, sunlight falling on the Earth's surface. Then there is a reflected solar energy. So sunlight, which is reflected from the Earth's surface, and of course, Earth has its own emitted energy. Remote sensing measures those all of those three types of energy. Also, important thing to understand when speaking about Earth observation is, of course, electromagnetic spectrum. Electromagnetic spectrum is a full range of energy waves that travel as light. It goes from very, very short wavelengths like gamma rays and X-rays to very long ones like microwaves and radio waves. Our eyes, unfortunately, can only see a tiny slice of it, which is called visible light or visible spectrum, from violet to red. But satellites or sensors installed on them can measure many other parts of the spectrum, like infrared or microwave, which reveal things we can't see, such as plant health, soil moisture, or even tiny movements of the Earth's surface. Unfortunately, atmosphere blocks some of the wavelengths, and remote sensing or Earth observation sensors are designed to use so-called atmospheric windows. So where atmosphere, so those parts of the electromagnetic spectrum which are not blocked by the atmosphere, for example, visible or infrared light or near infrared light and microwave. Different objects on the Earth's surface interact with this energy in a very different way. And it's important to understand which parts of electromagnetic spectrum are better or worse to be used to monitor different types of objects on the Earth's surface. So further, I would like to give you like a small overview on how this process happens. So let's start from vegetation, for example. Healthy plants absorb red and blue light and reflect a lot of green and infrared. We can't see infrared light. So this is why we see plants as green, but satellites, of course, can record this infrared light and detect this infrared light. And it's extremely valuable source of information to monitor state of any vegetation. Next one is water. Water absorbs longer wavelengths like red and near infrared and reflects a lot of blue. This is why we see clear water like dark blue or just blue, and the sediment-rich water would look slightly greenish or like more brighter and so on. So just by like clean water or like sediment-rich water or dirty water interacting with this type of radiation in different way, satellites can record it and we can see the difference and we can make conclusions about the state of this like water body, for example, like river, sea, ocean, and so on. Then there is soil. Bare soil reflects more in the red and near infrared than vegetation. Its brightness and color can vary with moisture, mineral content, and texture. And of course, satellites also are capable of recording this. Snow and ice strongly reflect visible light, especially in the blue and green. They absorb more in the infrared, making them appear bright in true color but darker in infrared bands, for example. And we will discuss further what is true color for those who still don't know. Atmospheric gases, so atmosphere, right? So atmospheric gases and particles absorb and scatter specific wavelengths. And of course, this affects how the solar radiation passes, creating windows for observation, as we mentioned before, and also signals of pollution or clouds. This is why Earth observation satellites can be used extremely effectively for monitoring of the atmosphere pollution. So everything which we discussed before, all these different types of bands and interactions with different types of Earth surfaces, in general, can be like all these different properties of different materials can be called spectral signatures, because every material reflects and absorbs light differently across wavelengths. And this unique pattern is called spectral signature, is like a fingerprint of each specific type of land cover or object on the Earth's surface. And even when they have different states, so for example, healthy vegetation, dry soil, wet soil, and so on, it has its own spectral signature. So there are specifically different bands of a satellite image or parts of electromagnetic spectrum which are more usable or more effective to monitor each specific type of land cover, let's say. And I was constantly mentioning things like bands or like layers and different names of parts of electromagnetic spectrum. And now I would like to explain you what it has in common with the satellite image, basically. The thing is that when we refer to a satellite image, it's not just one image. It's a stack of different layers. It can be 12, it can be 40, sometimes it can be even 300. And each specific layer of a satellite image records information about reflectance in each specific part of electromagnetic band. So it can be like ultraviolet, red, green, ultraviolet, blue, green, red, near infrared, shortwave infrared, thermal infrared. So each of these images, and it's usually grayscale image. So in the end, of course, we will see satellite image as a colorful one, but you need to do something with it, and we also will discuss it further, to make it more representative, more informative, to make it to make this image to show us specific things we are looking for. So it's important to understand that each satellite image is just not one image, it's a stack of images, and they're all equally important. And by combining them in different ways, or applying different mathematic equations to them, we can derive extremely precious, very useful information for different fields of science. So we will discuss closer to the end of this session how you can combine those different bands and extract this information and the math behind it. But before this, I would like to speak about atmospheric interference. The thing is that the atmosphere can, of course, distort signals. So before we start using satellite imagery for analysis, we need to correct the data to make sure that it reflects the surface and the real picture on the Earth surface properly and correctly. Good for us, we don't need to do it by ourselves because there are different levels of satellite imagery processing, which and all these different levels, imagery, which is already processed, is published. So you can select by yourself which level of processing you want to use for your specific case. This is an example of how these different processing levels may look like on example of Sentinel-2 data, for example. Sentinel-2 is a multispectral optical satellite. So here you can see an example of how it may look like. So when a satellite takes a picture, the very first data it sends down is a bit messy. It's so-called raw numbers, and this is something we would call level 0. Then, step by step, this raw data is cleaned, corrected, and placed on the right spot on the map, because sometimes there should be like a geometric corrections applied, geographic corrections applied, and so on, because sometimes satellites make images not 90 degrees above the ground, but under angle, and it distorts the image a little bit. So, of course, all these things should be corrected, but very, very nice for us that it's done by someone else, so we don't need to deal with it, but we just need to know that there are different levels of processing. So when we select the raw image for our analysis, we will select the very highest level, which is already cleaned for all possible mistakes, and we can really trust this data. So after this so-called level 0, which is raw data, step-by-step image would be processed, and we would get to something like level 2, and it would look much more like a normal image of the Earth surface, ready for analysis. On top of that, scientists create high-level products, things like maps of vegetation, health, or drought, which are easy to use for agriculture, environment, or planning. So basically, satellite image travels from raw numbers to usable images and then to ready-made maps and indicators. Sometimes on the internet you would find some maps of like deforestation or like vegetation stress or agriculture. So maps which already have some specific information, some specific indicators mapped. So those are so-called like high level products. But to get to that point, of course, you need to apply some algorithms, processing techniques, and so on. Another thing, apart from all those different processing steps, which are needed to be taken, related to the atmosphere and terrain and so on. There is another important thing, and it's a cloud cover. And why cloud cover should be considered? Because it's one of the biggest challenges for optical satellites. And again, if you still don't really understand what are the optical satellites and why we're speaking about it, we will open up this topic a little bit further. So yes, clouds are one of the biggest challenges for optical satellites. And the problem is that clouds block the view. Because again, optical remote sensing uses sun radiation as a main source of information, or Earth's own emitted radiation. And unfortunately, this type of radiation can't travel through clouds. So every time we have clouds, it means that we don't have any information from this area, from this place. So cloud-free images are extremely valuable. On this map, you can see the fraction of cloud cover from 2002 to 2015. And you can see that the least clouds are the least amount of clouds is depicted as blue, and the most amount of clouds in average in these different parts of the world are visualized with white. And from this map, we can make a conclusion that some areas of the world are constantly covered with clouds. So we just can't get any information from there if we are using optical remote sensing. And optical remote sensing is, for example, provided by Sentinel-2 or Sentinel-3. And it's basically making a photo from your phone while sitting on a satellite. So it's so optical remote sensing is like a normal photo. It's like making a photo, but if there are clouds, we just can't make it. So we can't get information from those parts of the world, never. But there is a solution for this. And this is active remote sensing. There are different types of sensors for Earth observation, for remote sensing. And they can be divided into two big groups. Those are passive sensors and active sensors. So as we discussed initially, passive sensors, they rely on sunlight, like optical satellites. So they don't emit any signal by themselves. They only record this radiation reflected from the Earth's surface or emitted by the Earth, right? But active sensors, like Sentinel-1, for example, it's a SAR satellite, or lidars or sonars, they send out their own signal. And it helps us to get information even when there is a cloud cover, fog, if it's night, because obviously in night there is no sun radiation, right? So there is no source of energy for passive sensors or optical sensors. So then we have active sensors, which have, of course, very different physics of image acquisition, but it's very different from optical remote sensing, but it provides extremely valuable source of information for different types of analysis. Apart from those two main groups, like passive and active remote sensing, those also can be divided into smaller groups. For example, passive sensors can be multispectral or hyperspectral, and active sensors can be like LiDAR, radar, and so on. Speaking about radar, all these radar satellites, or so-called SAR satellites, but not all radars are SAR, but it's all the same, like active remote sensing sensors. They operate on the microwaves. And of course, they have also different lengths of those microwaves. So for example, Sentinel-2 or Sentinel-1 would be like a C-band SAR, or there are some others which are S-band or L-band. And those are different bands, which basically, so this letter describes how deep this microwave sent by satellite to the Earth's surface can penetrate into different types of objects. So, for example, C band like Sentinel-1, it's good for monitoring like agriculture or like droughts and floods and things like this, but it doesn't really penetrate deep to stems of plants, right? So it's not very precise in calculating, for example, above ground biomass, right? So there are others like L-band, for example, L-band radars, which are more helpful because they can just penetrate deeper. So basically, this letter and in description of a satellite will tell you how long is the wavelength it uses and how deep it can penetrate into different objects. And when I mentioned that this active remote sensing sensors have completely different physics behind the image acquisition, I meant what you see on this slide now. So while passive remote sensing or optical remote sensing uses sunlight, which is reflected from different types of objects in different way from the Earth's surface, SAR, like active remote sensing, is based on the way how the emitted signal is interacting with different surfaces, depending on how smooth or rough they are, or the interaction would be also different in urban areas because there will be a lot of double bouncing, or in forest or dense vegetation there would be a lot of volumetric scattering, and relying on how the signal was scattered from different objects on Earth's surface, we then, after getting this image, can analyze it and understand what was the object, what was its state, and so on. And on this slide, you can see a comparison of two images, one from passive optical Sentinel-2, and another one is active SAR radar Sentinel-1. And you can see how different are those images. And they look different, and they show us different things, but they are extremely complementary because together they give us a fuller picture. Radar shows structure and moisture, regardless of weather, and optical satellites show us color and vegetation health under clear skies, and many, many other interesting and useful things and types of information. I saw that there was something in the chat, so I will take a look at it, and maybe there are some questions. Okay. No questions. Great. So we can continue. So yeah, and now I would like to move to multispectral and hyperspectral sensors. If it's a new information for you, you shouldn't be scared really, because it's just an overview. It doesn't mean that you really need to remember all of this and understand all of this. But it's just nice to know what types of information or sensors exist, so then you can understand what to look for and what to use for your processes or projects you are involved in. So now about multispectral and hyperspectral. So we mentioned that there are two types of passive remote sensing, or like optical information, multispectral and hyperspectral. And what's the difference? Basically, multispectral sensors capture information in a limited number of broad wavelengths bands, like Sentinel-2, for example. It has certain bands, and it makes it excellent for general monitoring of land cover, vegetation, and water, while hyperspectral sensors, on the other hand, they collect data in hundreds of very, very narrow bands across the electromagnetic spectrum, producing a highly detailed spectral fingerprints that allow scientists to tell apart materials that look very similar in multispectral images. And this level of detail is especially useful for applications such as mineral exploration, detecting crop stress, or analyzing water quality. In short, multispectral is like painting with a box of 12 crayons, while hyperspectral gives you 300 crayons and the ability to capture every subtle shade. Now I would like to discuss different types of resolutions, which it's very important to understand while choosing a data source, like a data source of satellite data, because obviously for different applications you need different, like cheap or free of charge or more expensive data sources. Meanwhile, again, I saw there was something in the chat and I checked quickly. So the question is, to follow the change of built-up areas, would it be better Sentinel-1 versus Sentinel-2? The both are valuable, because on Sentinel-2, so imagine that you've been able to take a picture of a city or a town, yeah, from an airplane every 7 days for the last 7 years, right? So you basically will see how it was expanding, what was added, like parks and buildings and so on. So you literally have this time series of change, and you can see how fast, when, and what was changing. But Sentinel-1 will provide you more like structural information about those changes. So both are useful to monitor built-up areas, but in a different way, from different perspectives, from different angles. So both are useful, but even Sentinel-2 is great for this. So, returning to types of resolution. Before we start speaking about it, I would like to discuss thing, which I believe all of you know. What is a pixel? Why pixel and understanding the pixel thing is important in the framework of Earth observation, because pixel is a structural unit of an image. And it's important to understand it before we start speaking about, for example, spatial resolution. So what is spatial resolution? It's one of 4 resolutions which we are discussing today, which is really important to understand and know the difference. So spatial resolution is basically as the size of 1 pixel on the ground. The higher resolution, the more detail, and the smaller area per pixel. So if we say that spatial resolution of a sensor is 1 kilometer, it means that in 1 pixel there will be an area of 1 kilometer on 1 kilometer, like averaged, right? And if you say it's 30 meters, it means that 1 pixel will cover 30 on 30 meters of real Earth surface. If we say it's 10 meters, it means that it covers 10 on 10 meters, so 100 square meters, and so on. And you can get satellite data with spatial resolution of up to like 15 centimeters per pixel, which is super high resolution. But this type of information is usually provided by commercial companies, and it's often quite pricey. Meanwhile, for example, Sentinel-2 provides you information where like most layers of the satellite image, the one I shown you before, has 10 meters per pixel. So it's like a great resolution and great level of detail for free, because obviously this information is publicly available, it's for free, and everyone can access it. Meanwhile, of course, there are some applications where you really need more high-resolution data. So, for example, if you want to monitor forests, or you want to monitor rivers or agriculture, 10 meters per pixel or 30 meters per pixel or 20 meters per pixel is more than enough. But if you are dealing with, I don't know, migration of polar bears somewhere, you need to really see the bears. Or if you want to monitor like the solitaire trees somewhere, and obviously one tree, you won't be able to detect one tree in a 10 on 10 meters in 10 meter resolution image, because it's literally 1 pixel and it's not really obvious what it is. Then of course you need something more high resolution, like 30 centimeters or half a meter, and so on. So depending on how big the object you want to study, you need to make a decision on what kind of spatial resolution the imagery should be for it to be useful for your project. Again, a little bit of an example. how the same object would look in different resolutions, like 5-meter resolution, 10 meters, and 30 meters. So let's imagine you want to study some kind of like water quality in a lake, and depending on how big is the lake, sometimes 30 meters is still can be enough. But if it's relatively small, it's better to get more high resolution data, because you will obviously get more information, more details about it. There is a question in the chat. Just a second. Okay, there is not a question but an answer. Great. Next type of resolution. So we discuss spatial resolution. Now spectral resolution. What is spectral resolution of a sensor? It's basically number and width of wavelengths bands a sensor can detect. The more bands, the more ability to distinguish different materials. So here we see a comparison of, for example, Sentinel-2 and Landsat bands. And while it covers more or less the same wavelength, so there would be like ultraviolet and blue and green and red and near infrared and medium infrared. Landsat, for example, also covers thermal infrared bands, while Sentinel-2 doesn't, but Sentinel-2 has more bands in general, right? But if you want to detect something which is related to ecosystem cooling potential, for example, or some other things where it's important to be able to measure like temperature of Earth surface, then of course you need to look towards Landsat data. Or sometimes commercial imagery providers, they have very limited number of bands. For example, Planet provides, their satellites or sensors, they don't provide you with near infrared or mid-wave infrared bands, which are the most valuable for monitoring of vegetation. They only provide you with red, green, blue bands, right? So if you want to study like health of vegetation or water content in soil and vegetation and so on, it's not very useful. So those things really need to be considered before you start using data set for your purpose. Another important thing is temporal resolution, and it's basically how often a satellite revisits the same place. The higher temporal resolution means more frequent updates. For example, Sentinel-2 has around like 5 days revisit time, and it ensures frequent data collection, which is crucial for monitoring dynamic changes. Temporal resolution is particularly important for tracking seasonal variations in vegetation, monitoring urban expansion over time, assessing the progression of natural disasters like floods and wildfires. This regular data availability allows researchers and decision makers to respond quickly to changing conditions, making satellite data extremely valuable. For example, as I mentioned before, Sentinel-2 has 5-day revisit time. It means that from the moment it was launched in 2015, it was every 5 days making an image of the same spot on the Earth surface. So it takes 5 days to the constellation of Sentinel-2. There are two, A and B, Sentinel-2 and B. So it's basically like two satellites. It takes them 5 days to make an image of the whole Earth, right? So every 5 days, the satellite returns to specific position. Some satellites have, for example, 1 day revisit, 1 day temporal resolution, such as Planet. I think it's called DAVS or something like this. Like Planet has like 1 day temporal resolution. Sentinel has 14 days temporal resolution. So you will get one image every 14 days. And there is also a very nice data source such as Sentinel-3. It has one day temporal resolution. So for example, if there is a flood happening or there is some kind of fire happening and it's quite big, you, instead of waiting for Sentinel-2 to revisit this area, because again, in 5 days, flood, fire event may finish, you can use data from Sentinel-3 because it has 1 day temporal resolution, but 100 to 300 meters spatial resolution. So it's really useful in terms of how often it visits the area, but it has lower basically level of detail than Sentinel-2, but it's a great data source, and again, it's for free. You can openly access it to monitor things like this. And the last type of resolution, which potentially you may never really need to know to select the data source for yourself, but it's a radiometric resolution, and it measures the satellite's ability to detect subtle differences in light intensity. So as I mentioned previously, all satellite images initially consist of many layers, and each of them are they are like gray, like black and white, so it's like grayscale image. And when we speak about radiometric resolution, depending on how big it is, so it can be 2 bits, 4 bits, 8 bits, and so on, or 16 bits, 12 bits. It depends. It says us how many shades of gray it can actually differentiate. So if it's 2 bits, it will be only 4 shades of gray. And if it's 4 bits, it will be 16 shades of gray, and so on. And why it's important? It's important because if we have very low radiometric resolution, let's use apples as an example, right? It means that we only can see all apples in the world, only yellow, only green, and only red, without any shades and like spots of different colors of them. But in reality, apples have many more colors, and the higher radiometric resolution, the more those like real details you will be able to detect using satellite imagery. There are some messages in the chat. I will check it really quickly. Okay. So are Sentinel-2 or 3 satellite images available for free across different time periods? Like they are in general available for free. So from the moment those satellites were launched, I don't remember unfortunately when Sentinel-3 was launched, but a couple of years ago for sure. And Sentinel-2 was launched in 2015. They are all available for free to everyone. The question. This question was answered already, thank you. Okay, so now let's continue with basic analysis techniques. And before we start speaking about it, I want to remind you again that satellite image usually consists of many images. Sometimes it depends on how it depends on spectral resolution. So how many wavelengths are covered by this sensor, and each of them is recorded into separate band. For different sensors, different satellites, the size of each covered part of electromagnetic spectrum can be different. Some are wider, some are narrower, but in general, they're all recorded in different bands. So it's a stack of images. It's like a sandwich where you can decide which one you want to leave and which ones you don't want to use. So here again, on example of Sentinel-2, we can see the list of bands, so list of parts of electromagnetic spectrum covered by each band, yes, the central wavelengths of this band, and the resolution. So Sentinel-2 image has different resolution depending on the band you're working with. It can be from 10 meters to 60 meters. But in general, most of the really useful ones, which you would use in most cases, they have resolution of 10 or 20 meters. For us to understand better how it looks like, I want to show you an example of each and every band of an image of a Polish town made by Sentinel-2. So this is how band 1 would look like. It has spatial resolution of 60 meters, and you can see here the central wavelength is 443 nanometers. Then there is band 2, which is blue, and it has 10 meters spatial resolution. So we already see the difference. And also, I would like you to pay attention to how different length cover types are how differently they look in all those images. So then we have band 3, which is also 10-meter resolution. Then we have band 4, red, and you see the vegetation looks slightly different because we already know that vegetation interacts with this like near infrared green light in different way. And then we also have band 5, which is also 20 meters. And also we can see differences, right? That some objects are more defined, like more highlighted in some bands, and some are less, right? So different spatial resolution, first of all, different interaction with this part of electromagnetic spectrum gives us different image. So here again, comparison, Sentinel-2, different bands, different spatial resolution, and different spatial resolution. And again, we are reminding ourselves that each image consists of pixels, and each of those pixels, they have some kind of value. Let's call it the amount of radiation which was recorded from an area covered by this specific pixel, right? And there will be some kind of value, some kind of number, depending on how big the radiometric resolution, because if it's 2 bits, it will be only 0, 1, 2, 3. If it's 16 bits, there will be many shades of gray or like numbers, but each pixel has its own number. But then if we take at least 3 bands, 3 of these grayscale images, and we put them together, we can get a colorful image. All digital screens are using RGB color model to display color. And if you assign to this red, green, and blue channels of every digital image some kind of number, depending on this numbers, it will show you different colors. So by combining any 3 layers of a satellite image, we can get a colorful image showing us different types of information, highlighting for us different types of information. And the amount of shades of colors in this image, again, will depend on how big is the radiometric resolution of an image. And in the very beginning of my presentation, I referred to something calling a true color image. And here you can see an example of a true color image. And again, as you remember, I mentioned at the beginning that human eyes can only see this part of electromagnetic spectrum, which is called visible light, which is red, green, and blue. If we speak about satellite images, so if you combine in these 3 channels, red, green, and blue, you will get image like this, which looks like you would see an area from an airplane with your own eyes. But if we take out one of those bands or parts of electromagnetic spectrum and substitute them with a part which we normally don't see with our own eyes, we would get something which is called false color image. And it would look completely differently from how we usually see things with our own eyes, but it highlights some important properties or features which we normally would find complicated to see by ourselves. And there are different combinations of bands, for example, of Sentinel-2 or Landsat or any other optical or passive sensor. And depending on what kind of features you would like to combine or you would like to highlight or see or delineate, you can use different band combinations to do so. So this is like the basic thing in terms of like Earth observation, images, interpretation, and analysis you can do by yourself very easily. It doesn't require any specific knowledge. And if we have a little bit of time at the end of this session, I will show you free of charge online tool where you can easily access all this imagery, visualize it, and start using Earth observation today already. This is another example of a so-called false color image combination, which uses not red, green, and blue parts of electromagnetic spectrum, but some others. And this specific combination, for example, helps us to delineate and highlight, see better some urban features. In general, there are different bands combinations, and if you want to learn more about them, you can just Google Sentinel-2 bands combinations, and there will be information about which bands to combine and what they are useful for. But next, very important, very interesting, I would say, level, but still not very complicated, of satellite images processing is spectral indices. Spectral indices are basically combinations of spectral reflectance from two or more wavelengths, and spectral reflectance is basically this number inside the pixel, and the wavelengths are the layers of satellite image. And these spectral indices can indicate the relative abundance of features of interest. For example, there are vegetation indices and some other indices, and there are also there is also a group of indices which is called normalized. For example, NDVI, NDMI, which are like vegetation index or moisture index, and water index, and so on. There are like a lot of them. There are thousands of different indices. There are libraries of indices on the internet, so you can easily Google it, and you can see that you can, depending on how you're combining values from different layers of satellite image, you can get huge variety of different metrics and information and so on. But today, specifically, I would like to speak about things like NDVI, which is vegetation index, and NDMI, because those are cornerstone, for example, for monitoring of vegetation, for agriculture, for forestry, for nature conservation, and so on. So little bit of preparation for us to be able to understand how this information is derived, how this information is derived, what it's based on, and why we can trust it. So again, here you can see this example of a formula which is used to calculate indices like this normalized different indices like vegetation, chlorophyll index, like moisture index, and so on. So we can see that we need here some kind of A and B, so two layers of satellite image. So we have two layers, they are grayscale ones, they consist of pixels. Each pixel has a value. So then we just apply one by one each pixel from two of those to that formula, and we get some kind of number. And this number represents, for example, if we take near infrared and red layers of a satellite image, this number represents the amount of chlorophyll or like health in vegetation. And it can give us a lot of insights about phenology phases or vegetation stress and so on. And it's really a cornerstone of many private companies selling this type of insights to farmers, for example. It's literally a cornerstone of their business, just calculating things like NDVI or moisture index. And specifically speaking about NDVI, it has, because it's normalized difference, it has values from -1 to 1, where 0 is bare soil. Everything above 0 corresponds to vegetation, and the closer it is to 1, the more dense and healthy this vegetation is, the more chlorophyll it contains, and so on. And everything below 0 corresponds to man-made objects or snow cover, ice cover, water bodies, or built-up areas, and so on. And even in this image, you can see that agricultural fields are like different shades of green, and then we see this built-up area and the river, and they are white and yellow because those are non-vegetation objects, right? And here you can see an example of how to read or understand NDVI. What it shows that, as I said, like bare soil, and then man-made or like water bodies or snow, and then depending on the values above 0, you can make a decision on how strong and healthy mature plants are. And it's all based on the fact that this index is calculated using near-infrared and red bands of electromagnetic spectrum. And as mentioned initially, plants, when they are healthy, they reflect more near-infrared than red. And when they are not healthy, we even see in the autumn leaves are more green and yellow. They reflect more red and less near. And on this simple physics, this index is basically built. Again, how it's being calculated, because you would see a lot of maps like this, like NDVI or NDMI maps, this type of indices maps. It's basically we take two images, which are grayscale, each of them has pixels, some values, put in a formula, just make simple calculation, and then we get this type of value, and this basically represents the NDVI index and the vegetation health. Then another interesting type of index, which is calculated in the same way, is normalized difference moisture index. It just uses the same formula, but different bands, near infrared and short wave infrared. The same has the same scale from -1 to 1, and depending on how moist is something, the soil, the vegetation, or you can even monitor floods sometimes using this index. It will show you higher values, and if something is more dry, there is more water stress and so on, it will show lower values. As I mentioned, there is huge amount of different indices. You can calculate all sorts of things using a different combination of satellite image bands, and this information can show you completely different things. Now, a small overview of like slightly more advanced ways of satellite or approaches in satellite image processing. So there's something which is called change detection, and when you hear this, it basically means that we have like a repetitive measurement. It can be just an image, like true color image, or it can be like a map of NDVI index or NDMI index or any other. So, like that we have, it means that we have like repetitive measurements on the same area of interest, and we just comparing it, and we are detecting change, and this is change detection. Sounds very smart, but yeah, in reality, it's just it. And another thing which also quite interesting and useful is satellite image time series. It's basically when we are using a stack of repetitive measurements for the same area, and we can analyze, basically we can like make time series, and we can analyze trends and changes, and we can analyze phenology phases of vegetation and many other things. And another and the last one for today, important one, because you are all from the field of statistics, and I believe that often you see the land use, land cover maps, and maybe sometimes you question like, are they really precise? How they've been done, and can we trust them? But those maps, those land use, land cover maps, if we speak about it in a very simple way, they are based on satellite image classification. It's because each type of objects, how it's done basically, yeah? Because each type of land cover has its own spectral signature, as was mentioned in the beginning. It has different properties, different colors, and interacts with like signal or sun radiation in a different way. And there will be different numbers, like different numbers in pixels, because it will be different amount of this radiation recorded. And then by applying some statistics and mathematical equations, we just divide, we do segmentation of these pixel values, right, into different groups. And then we assign names to those groups, and this is called classification. So most of these LULUCF maps, and use and cover maps, produced by many states, is using this approach, basically, if we speak about it in a very simple way. Because of course there always will be like additional data sources, like a field data, combinations of several sources of satellite imagery, not just one. And then it provides really, really precise information. So from my side, it's all from today. For today, I would like to know if there are any questions. If there are no questions and people are not too bored, we can take a look at Copernicus browser. So
maybe just give 1 minute, Natalia, just to see if anybody raises a question in the chat. I don't see anything at the moment, and we've been answering as we've gone, and I'm quite happy to see as well that some of the participants have been answering as each other as well, which is very good. So maybe what we'll do then is, Natalia, maybe if you could give your quick introduction to Copernicus browser, and then in the meantime, that gives people a chance to raise any last questions that they might think of.
Okay, just give me a second. So I would ask you all to just put in the Google search Copernicus browser. And I guess the very first link will be it. And you need to register there. It's very quick and it's for free. It doesn't cost anything. It's a very easy, free of charge online tool to access and do basic analysis of Earth observation data. Just a second. Do you see my screen? Yeah?
Yes, we do.
Yeah, okay. So this is Copernicus browser. You need to log in. You can use it even without logging in, but it just gives you access to all functions where you're actually logged in. So here we can see different data sources, data collections. For example, you can select, I want to access an image from Sentinel-2, for example. Or there are others also. There are Sentinel-1, Sentinel-3, Sentinel-5, and a little bit of others datasets. Here, for the first thing we will see is whether we want to visualize Sentinel-2 L1C or L2A. L2A is the highest possible level of processing. So this is like analysis-ready data. So I would prefer this. Also, it says, please zoom in or search for a location of interest for this service to be able to show you the latest Sentinel-2 images, Sentinel-2 image for this territory. We have here a little bit of Italy, for example, and we can select. We want to like visualize like a single date or like in between dates. I want some kind of single date. And also, apart from this, we immediately see some clouds because there is a cloud cover because it's winter and winter is famous for being quite cloudy, the same as autumn. So I would apply this cloud cover filter because we discussed cloud cover with you, right? That for optical imagery, it's not a big friend, it's an enemy. So usually I would recommend you to use like around 20% cloudiness maximum for analysis. And we would see here highlighted in like pink or beige dates when an image was acquired for this territory in general, but with like more blue squares, you would see dates when the image was taken and it had less than 19% in my case, percent cloud coverage. And here it is. So I just selected one image, which is covering this island. And you can see how these images are done in stripes, and each like bit of the stripe, it's like if you cut it into squares, it will be something which is called like scene, like a scene like recorded by a satellite. And sometimes to cover your area of interest, of course, you need more than one scene. You would need like two scenes or even more depending on how big is your area of interest. But in general, here it is. So it automatically shows us this image in true color and combination. We can zoom in. Some questions. Okay, they were answered, as I see, those questions. So we can zoom in, see how it looks like. Here you are, Sentinel-2 image. We can do some simple visualization. For example, this false color we discussed during the introduction to EO part. There would be a description, or you can like immediately calculate NDVI for this area or moisture index and see if there is which fields are currently suffering from water stress. And there are some other ones which you can read about just by clicking here. Speaking about NDVI and time series, so here you are, we have an image of Sicily for 2nd of December 2025, and for some reason we want, for example, time series of NDVI values. And if you create an area of interest, for example, like this, again, it's a very simple tool, don't be angry at me that I'm showing it to you, but for those who want to have this first touch of Earth observation data, this is a great thing to use. So we can create area of interest, and then we can build a chart of values, and those will be NDVI values for this specific area for the last 1 month, 3 months, 6 months, and so on. So let's build, for example, for 1 year. And here, all images are taken into consideration, even if they're completely covered with clouds. But we remember that clouds, they block information. So it's better to use images without clouds at all, or at least with maximum 20% cloud coverage to get more honest and more real information. And when we changed our filter, we can see that the curve changed, and it shows us basically how vegetation conditions were changing inside this area of interest for the last 1 year or 2 years. You track the phenology phases and so on. The same thing can be used, the same simple approach can be used to, for example, to monitor like bark beetle disturbance or some health issues in plants and trees in the forest, and many other things. The same you can calculate, for example, this moisture index or some others. You can try to create some custom visualizations. Again, we discussed today some composites, composites meaning composing 3 different layers of a satellite image to get some specific visualization. So easily here already you can try to do it and see how it will change. You can Google about different band combinations, or you can create your own index. It can be this type of normalized different index like NDVI or NDMI, or some other types. And of course, there is a possibility to make some custom scripts and create some custom visualizations. This service, this Copernicus browser service, is great if you want to quickly download some images of something, for example, to use for your report or presentation, present it to your colleagues, to very quickly export some time series, because the previous chart of NDVI values I've shown you can be easily exported as a CSV file. So it's like just to have this first touch of Earth observation data, to do some basic things, and just to maybe just check how different things look, how different things look like in satellite images, and so on. This is basically it. And there is a question: is pixel grid perfectly aligned for time analysis? And answer is yes.
Yeah. There was also a question, Natalia, about the main segmentation methods.
Well, there are a lot of them, and I don't know. Nowadays, like different machine learning and AI methods are used for more precise segmentation. So there are like really a lot of them.
Okay. There was also a question raised or a comment raised around quality measures for maps. And I think this is actually one that we don't really intend to discuss here, but it's worth flagging because this is actually an example of what we would like to get out of the dialogue, is to understand the criteria that are important for statisticians and what might need to be adapted within the Earth observation processing chains or metadata in order to better adapt it for your needs. So this is one that I think we can't answer now, but we would be very keen to discuss this one offline.
So the question is, how precise are those maps? Yeah, basically.
Yes, but I think there's also specific criteria.
Well, the thing is that, again, like when we speak about land use and cover maps or similar maps, right? So there is some kind of classification methodology or algorithm applied to satellite imagery to build those maps. And then they get them in the end. It's not just like they're being published, like, without any check. So how it usually happens, for example, a random data set of 2,000 points, random points, would be generated across the all area of interest, and then people manually using very high resolution data like drone data or even going there personally, so field data. So this classification results derived from satellite imagery would be validated in this way, and then there will be like basically like a matrix build of like error matrix, and usually for those like LULUCF ones, the precision should be, I think, around 80, 85 or 90% minimum. So from those 10,000 randomly generated points, for example, 90% of them should really correspond to what was classified from satellite images for this map to be released, and they say that, well, yeah, you can trust this information. And usually in the metadata of such data sources, there will be stated a precision of classification of each and every land cover type which is present inside this map, basically, if it's speaking in simple way.
Yeah. Natalia, I'm afraid I think we have to stop there because we are running out of time here. It's a pity because this is actually a very important discussion which I think we need to have, and I really encourage anyone who's interested to contact me offline about this. We would also like to make this very much a two-way thing and also be learning more about what the statistical community needs and what criteria you need to assess. I'm afraid we've come to the end of our time, but I do want to highlight that there is another session next week, which will be a practical session, mainly around the use of QGIS and Copernicus use cases. So please do come back and join us again next week. There will then be a further session the week after where we will present some practical applications that have been developed within the Earth observation community. Other than that, I would like to give a very big thank you to Natalia. She's been talking for a long time, so I think her throat must be very sore by now. But thank you, Natalia. And thank you to everybody who attends. We hope to see you again at the next session, and we hope that you will feel free to contact us in the meantime if there's anything else. So thank you to everybody, and talk again soon.